Hello, AP Statistics. I'm going to be going over Chapter 22 notes with you, comparing two proportions. This is, the process is the exact same when we did a one proportion Z interval or one proportion Z test, except for now we're comparing two proportions. So just a couple things that I want to kind of forewarn you about that you want to watch out for. First of all, favorite band, Leftover Cuties. If you don't know them, check them out. Okay, a couple things that I want you to look out for. Always specify the order in which you're comparing. This is going to make a little bit more sense when we get further on, but you always want to specify the order, and you want to make sure that you write your variables so that they actually make sense. So, for example, if I'm talking about comparing the proportion of men to the proportion of women, I'm going to use little subscripts to help me indicate what I'm talking about. Just like if I'm dealing with proportion of green M&Ms and I'm comparing them to the proportion of green Skittles, I want to make sure that my subscripts indicate what the variable is that I'm talking about. This is really going to help you out a lot later when you're making your model and when you're trying to interpret your model. So a sampling distribution of your P1 minus your P2 is really what we're looking at now. So one sample statistic minus the other. So it's the difference of your sample proportions is what we're looking at. And we're trying to estimate the difference of our population proportions. So a couple things that hopefully will bring us back. That if I'm looking at the difference of two sample proportions, I'm actually going to do this on the side. I know it's written right here, but I'm going to write it on the side to make it a little bit more understandable. Let's say I am talking about green M&Ms, and I wanted to figure out what the standard deviation was of that. So I could have the square root of my sample proportion of green M&Ms times Q hat of my green M&Ms divided by the size of my M&Ms, okay? Now, if I was talking about Skittles, then I'm going to write this just a little bit below. So remember, this is my standard deviation of my sample proportions of green M&Ms. Now, if I was comparing the standard deviation of my sample proportion distribution of green Skittles, that would look like this. Now, recall back, if I wanted to look at the difference of those and I wanted to figure out the model, I would want to find out the standard deviation of the difference of the two. So my green M&Ms, let's say, minus my green Skittles. Well, two things I want you to remember as soon as I write that. First of all, we always have to take things into variances. I cannot do any operations with standard deviation. That's number one. Second, variances always add. They never subtract. So if I wanted to look at the variance, and I'm going to kind of do this in another color, of my green M&Ms, the variance of my sample proportion of green M&Ms just looks like this. I just squared it. So I got green M&Ms. Of course, I'm running out of room here. And Q hat of green M&Ms all over M. And if I wanted to look at the variance of my Skittles, I have variance of my sample distribution of green Skittles, and that just equals P hat green Skittles, Q hat green Skittles all over N. So, knowing that that's my variance, if I want to get my standard deviation, remember it all adds, and so I'm going to just kind of put a little line here. I would add my variances. Okay, so I'm going to put a big equals, but I'm going to notice this is my, oops, M&M's here, forgot my little M there. Notice this is variance at this point, but I want standard deviation, so I'm going to add a good old square root, because every standard deviation requires a square root. Okay, and that's how you get the standard deviation, but the difference of two proportions. Now, the third and final thing that you should remember about this is, going back, number one, you have to deal with variances. 2, variances always add, and 3, you can only deal with it if you have independent groups. So your populations need to be independent of each other. Okay, so that's actually 3 things I want you to remember when we do this. So going back up to the notes here real quick, if I look at what I just circled in green up here, notice that's your variances. Variances always add, standard deviations do not. And if I want the standard deviation of this, I would top it off with a nice square root. Okay? Now, when our samples, I'll do this in pink, when our samples are large, the distribution of p hat tends to be approximately normal. That's really cool because it's nice to be able to use a model to help us to make predictions about what's going to happen. It's our tie between the imaginary world and the real world, okay? Imaginary world of statistics. Our confidence interval for the difference of our proportions is very similar to what we've been dealing with. It's just our point estimate. So I'm going to actually underline this. So this is our point estimate. It's just the difference of our 2 proportions. Our critical value, whatever it is, times our standard error. Okay, so our point estimate plus or minus our critical value times our standard error. It's exactly the same as it was with a 1 proportion Z interval, okay? But this one's going to be called a 2 proportion Z interval. Now, in order for us to be able to use that normal model that we love so much, we need to make sure that certain conditions apply. So, same as when we did with the 1 prop. We need to make sure that we have a random sample from both populations, that the samples are independent of each other. Within each sample, there's also independence. However, when we sample without replacement, we need to check that the samples are less than 10% of the population, and we need to check the success-failure condition for both samples and make sure that they're 10 or more. Now, there is a little bit of leeway with this because sometimes instead of 10 or more, people say 5, but stick with 10. Alright, so that's a 1 proportion Z and 2 proportion Z interval. Now looking at the significance test for a difference of 2 proportions, so a 2 proportion Z interval, same exact thing as a 1 proportion. We would have our statistic, which notice our statistic is just the difference of the 2, minus our parameter, and I'm going to put a 0 in here and I'm going to explain why in a second, all divided by our standard error. Now, this looks a little different. This is because this is a pooled sample proportion. So that'll bring me back to this 0 here. Now, your calculator will only calculate a 2 proportion, that was my knee, a 2 proportion Z-test when the difference of the 2 proportions is 0. That's not always going to be necessarily true. But generally, with a 2 proportions Z-test, your null hypothesis generally is that the proportion, so P1, is equal to the other portion. I can rewrite this by subtracting P2 from both sides and getting P1 minus P2 equals 0. So the difference of our 2 proportions is 0. That's our parameter. That's how we got this 0 right here. Now, that leads me into looking at this standard deviation here. If we assume that the 2 proportions are equal, remember that's the parameters, the 2 are equal, we can pool our proportions together. So a pooled value is simply when so I'm going to say a p hat pooled is simply when I go ahead and I add the number of successes from my first to the number of successes from my second and I add their sample sizes as well. And that's pooling it. So that would give me p hat pooled, and then in order to get q hat pooled, I would just take 1 minus p hat pooled. Okay, so that's a pooled value, and if you want to read more about that, that's in your book a little bit. But we pool it together because if we're making the assumption that the parameters are the same, then we can make a stronger standard deviation by pooling it together. So remember, when you have, oops, I just noticed I did a little boo-boo here. This is N1. Remember, when your sample size is bigger, your standard deviation is a little bit more accurate. So that's why we add them together. So the assumptions are exactly the same as they are for a 2-proportion Z interval. You have an SRS drawn from both populations. The samples are independent of each other. Within each sample there is independence. However, when sampled without replacement, we need to make sure that the samples are less than 10% of their population, and we have to check success failure for both of the samples and make sure that they're 10 or more. So let's do some examples here. So let's go through this example. I have a salesman for a new manufacturer of cellular phones, and he claims that not only that they cost the retailer less, but also that the percentage of defective cellular phones found among his products will not be higher, and the percentage of the defectives found in his competitor's line will be. To test the hypothesis, the retailer took a random sample of each of the manufacturer's products, and then the results are in this table below. And we want to find out, is there evidence that the salesman's product had a higher defective rate than the competitors? And we're going to test at a 0.05 level of significance. So just as a reminder, 0.05 level of significance means that we're using an alpha value of 0.05. Which means that if, when we're all said and done, if we have a p-value that kind of crosses that threshold and is less than 0.05, then we're going to reject the null hypothesis. However, if it's greater than that and it doesn't hit into the rejection region, then we're going to fail to reject. So I kind of started setting this up a little bit. So we have a table. The number of defective was 21. Number checked was 180. For the competitor, 11 were defective and 180 were checked. And so the null hypothesis is that the proportion of the salesman equals the proportion of the competitor. So remember, your null hypothesis will always include an equal sign. The alternative is that the proportion of the salesman is actually greater than the proportion of the competitors. Proportion of defective. So I like to rewrite my null hypothesis so that I can actually look at what the model is saying. So I have the proportion of the salesman minus the proportion of the competitors is equal to 0. That's your null hypothesis. The alternative is that the proportion of the salesman minus the proportion of the competitors is greater than 0. Okay, and I always like to write it so that it's on one side, so that I know exactly where my model is going to be centered around. So we're going to check the assumptions, and the first one I like to check is that the sample sizes are large enough. So I'm going to check that the size of the salesman, and of course notice in this case I don't have a p to actually test it with. So when I was doing a 1 proportion Z test, I said if you have a p, always use a p. But here, I don't have a p. I just have the differences of my 2 proportions. I don't have an estimated value for either one of the parameters. So I have to use p hat. So I'm going to look at the sample size times the p hat of my salesman. And I know in that case, it's 21. And then my sample size times my q hat of the salesman. In that case, I know it's 159. And then I'll use my sample size of the competitors times the p hat of the competitors, and I know that that's 11. And then the sample size of the competitors times the q hat of the competitors, And I know that that is 169. And I'm going to just kind of put a little bracket here because I didn't give myself enough room. And I'm going to say all are greater than or equal to 10. So therefore it's large enough. I know that the size of my salesman's ones, the check, the 180, and the competitor sample size are less than 10% of the population. It was stated that it was a simple random sample. And then also, the population of the salesman's phones and the competitor phones are independent of each other. So now I can move to name my test. So the test that I want to do here is a 2 proportion, and I know I'm going to kind of cross off this p-value because I ran out of room. But I'm good to go with a 2 proportion z-test. Remember, all the conditions do for me is allow me to be able to use a normal model, which allows me to be able to test where I would see this sample of difference of proportions if I was to put it on a normal model. So my p-hat of my salesman's phones is, remember that's, and I'll write this out, is always indicated as my x of my salesman all over my n of my salesman, which here would be 21 over 180, because I was actually given the numbers, and that is 0.117. Of my competitor, remember that's the x of my competitor all over the n of my competitor, which equals 11 over 180. Again, I was given the numbers, so I didn't have to backtrack with the percentages to figure out what those numbers are. So I have 0.061. And since I'm doing a 2 proportion z-test, I'm going to pull together my p-hat because I've made the assumption that they're equal to each other. So my p-hat pooled is going to equal 21 plus 11 all over 180 plus 180, which is just going to equal 32 over 360. Putting that in my calculator, I get 0.089. And that's my pooled amount. I'm going to draw my model down here since I was able to use a 2 proportion z-test. So drawing in my normal model. And then remember in the beginning I said it's going to be very important to indicate the direction of your subtraction. So in this case my model represents proportion of salesmen minus proportion of competitors. So I always write that in the corner. The difference of the two as a parameter we found to be 0. And I want to see where the difference of our p-hat salesman minus our p-hat competitor lies. So the difference of those two, I got 0.117 minus 0.061, 0.056. I'm going to erase this for the conclusion because I don't have my standard deviation either. So I'm going to figure out my standard deviation of my p-hat pooled. And remember, going back to the formula up at the top, I don't give you enough room. Times, oh my goodness gracious, I do not give you enough room. Ah. One plus 1 over 180 plus 1 over 180. Oh, my head. There we go. Standard deviation of p hat pooled. Definitely didn't give you enough room. And of course that equals 0.030. Let's just go with that. All right, so the difference here is positive, so I know I only have to fill to the right. So I'm going to go over here, 1, 2, 3. My first standard deviation is 0.030. My next one would be 0.060. Breaking things. If I was to plot in the difference of my two proportions, 0.056, it's going to go about right here. Remember that's 0.056, and I want to know the probability of being greater than that, so I'm going to shade to the right. So, what do I need to find? Of course, I need to find my z-score. So I'm going to use the magic of additional paper here and find my z-score. So I have z equals, well, remember it's the difference of my two sample proportions here. That's my statistic. I'll put that in parentheses. Minus my parameter. All over, in this case, it is my standard error of p hat pooled, which equals 0.056 divided by 0.030, which gives me a z-score of 1.852, if I've calculated correctly. Now, remember my p-value, I'm going to keep on going down here on the right. My p-value is just what's the likelihood of getting this as a score or greater. So is the probability of getting z greater than 1.852. And so in that case, I'm going to use my calculator, stick it in, go to here, go to my distribution, normal CDF, 1.852, comma 99, and I get 0.032. So as a conclusion, right, with a 0.032 being less than our 5% significance level, I'm going to reject. So my conclusion is, we would say, we reject the null hypothesis at the 5% significance level with a p-value of 0.032. There is evidence that the salesman's phones have higher defective rates than the competitors. Now, notice all this work here, and everything that I showed is pretty necessary. If I look here, and of course I just noticed a mistake. That should have said standard error of your p-hat pooled. Sorry about that. You need to draw in your normal model. You need to indicate the direction of your subtraction. You need to clearly indicate what your sample proportions are. You should always write out what your pooled value is. I calculated my my test statistic over here, which was my z-score, but you need to write that you're calculating out your z, and you need to write out your p-value. Now, you can do this test on your calculator, though. So if you go to Stat, go over to Tests, and notice number 6 is a 2-prop z-test. I'm going to kind of scroll up a little bit on this so that I can get my information clearly. Put it in here. And my x1 is 21. My n1 is 180. And then I've got 11, 180. And now, which way am I going? So notice my symbol was that the salesman's is greater than the competitor. So I'm going to choose the last one here being greater than. And of course, I love drawing, so we can draw, but let's calculate first, actually. So if we calculate, it gives you a little bit more information than the one proportion z-test. So you still get your z-statistic, which I have here, 1.85. Here you get your p-value. So notice it says p-value 0.032. And notice you get 3 p-hats now. Your first p-hat is, of course, your salesman right here. Your second p-hat is your competitor. And then the third p-hat right here is your pooled value. So notice our pooled value is that p-hat. See that arrow to the side? That means that there's more stuff to come. So I'm going to scroll down, and the only 2 other pieces of information it gives us is our sample sizes of both of our samples. So I had 180 in the first sample, 180 in the second sample, and that's the only additional information. So for shins and grins, let's go back to drawing it. So I'm going to go 6. All the information's in. So I'm going to go to draw over here because I love drawing my picture. Draw it out. Notice it shades it just like I did. Shows me my p-value, shows me my z-score. Those are important pieces. So notice with your p-hat pooled, you can just show what the addition is that you're doing and then just give your number that your calculator gave you. Same with your first sample proportion. You can just write in that ratio. Second sample proportion, write in the ratio. When you do the test and you calculate it, you can just write the numbers in after. No need to go ahead and figure it out. When you're dealing with your standard deviation of your pooled, you could just write in your numbers and then, and that's fine. You don't even need to calculate it. I just did. When you do your z-score, as long as you write this piece right here, you're all set. Okay? And then you have your conclusion that you need to write. Now, while we're on this problem, just really quickly, let's do a 2 proportion z interval since we have the information all in here, and then we can go ahead and analyze what that actually means. So I'm going to go to test. Now I want a 2 proportion z interval, so I've got to go down a little bit. So 2 proportion z interval. Here we go, which is letter B. All my information is in, so I'm going to go ahead and calculate that. And my interval is 0.00645 to 0.10466. So I'm going to actually write that down, just take a little screen capture here. So with this one, we had a confidence level of 90%, which gives me a critical value of 1.645. And the conditions were all checked, so we did a 2 proportion z interval. And now notice the numbers that we get. Those are percents. So our conclusion would be we are 90% confident ooh, geez, spelling. 90% confident that the number of defective phones from the salesman. Now, I only know that it's the salesman because we wrote what the direction is that we did it. My P1 was salesman, so I did P had a salesman minus competitor. So the first person I'm going to mention is the salesman. The number of defective phones from the salesman is between 0.6 10.45% to 10.466% greater than the competitors' firms. Okay, so notice you're talking about comparing two things, salesmen's phones to competitors' phones, and the percentage that I get is actually describing that difference. So if I want to go ahead and verbally describe the difference, I want to say that we are 90% confident that, spelling counts, the number of defective phones from the salesman is between 0.645% to 10.466% greater than the competitors' phones. Now, I know that it's greater because both of these are positive. I could have gotten a negative number, and in that case I would be negative or less than to greater than, or both being less than the competitors. Okay, and the other thing I want you to know is 0 is not included in here. So that supports our hypothesis that the differences aren't equal to each other. Because if they were, I would have had a 0 in there. All right, so the next example, I'm going to actually kind of do on the next page. So in this case, and I'm just going to code it down a little bit more, we have soap. And so you're just going to have to read this sheet, just stick with it. So you have a survey of 300 people from City A, and 128 of them prefer New Spring soap to all other brands of deodorant soap. And in City B, you have 149 people of the 400 preferred that New Spring soap. So we want to find a 98% confidence interval for the difference of the two proportions. Before I get started, I want to check my conditions to make sure that they can be satisfied. So I can use a normal model. So I'm going to check my sample sizes. So I'm going to test from City A. So I have number of people from City A times the proportion of those that like New Spring soap from City A. And that was 128, which means that those from City A that didn't like New Spring soap from City A had to be 172. Those from City B that liked New Spring soap was 149. And those from City B that did not like New Spring soap from City B was 251. All of these, all are greater than or equal to 10. So we're satisfied there. Samples were simple random samples. We can say that City A is independent of City B. Very important in order for us to figure out the standard deviation. We're hoping that 300 people, because it is a city, is less than 10% of City A's population. Generally, if you're a city, you have to be so many people. I think it's like 15,000. Maybe it's 30,000. But hopefully it's bigger. If not, we're hoping that at least there's 4,000 people. So we have 400 for less than 10% of City B. Okay. So with conditions satisfied, we can use a normal model, which means that we can do a 2-proportion Z interval. Now, when I'm doing a 2-proportion Z interval, notice I'm not assuming that the proportions are equal. No, I'm not. So I cannot combine the samples together to come out with a p-hat pool value. I can't, because I'm not saying that they're equal to each other. I'm saying that they're separate. So I'm going to go ahead and construct my 2-proportion Z interval just by using my standard error of the difference of the two proportions. And so I'm just going to show you what that looks like all done out. So my first sample proportion, which of course notice I'm going to put up my direction here. I'm doing city A minus city B. It's good to note your difference. That's going to help you with your conclusion. So that's 42.7% of city A preferred new spring soap, minus those in city B that preferred new spring soap, plus or minus. Now notice I wanted to do a 98% confidence interval, so the critical value for 98%, you could look on your tables, you could go ahead in your calculator, you could look in your book, but you're going to get 2.326 times standard deviation. So we've got 0.427, 0.573 all over 300. And then we've got 0.373, 0.627, so p hat q hat all over 400. Notice we have to turn them into variances. We're looking at the difference of those, which means that we have to add, because variances always add. And when we do this out, we get minus 0.0329, comma 0.1412. And these are percents. Now notice we have a negative. That doesn't seem normal, right? But when we interpret this, and notice we're interpreting as the difference, right? So we're explaining and comparing the differences between the two. We would say we are 98% confident that, in this case now we're talking about people, the number before we were talking about phones, of people in city A, that's why describing this difference up here is so important, that prefer new spring soap. Is between 3.29% less than, that accounts for that negative sign, and 14.12% more than, notice the other one wasn't negative, the number of people in city B. Okay, so at this point, if I was to ask you, if I was to do a 2 proportion Z interval, would we reject the null hypothesis that the 2 proportions are the same, or would we fail to reject the null hypothesis that the 2 proportions are the same? And if you said fail to reject, you would be correct, because notice 0 is included in this interval. So the 2 proportions could be the same because it could be 0. All right, so this is 2 proportion Z intervals, 2 proportion Z tests, and make sure that you get some practice, reread the chapter, go through some of the problems, and make sure that when they do sample problems in the book, that you actually look at them. Thanks and enjoy.